Slideshow mode. Okay.
Yep, that works.
Thanks, Damien. So what I'll be talking about today is a little bit of research work that we've been doing on controlling 100% inverter-based resource grid. There are some points here which will actually be a nice continuation of some of the key points that Nick brought up, although not explicitly focused on wind turbines, but the associated impacts that occur on the mechanical side and how they need to be, in a way, considered when we are planning the system for the future. And then just other aspects related to how we transition from battery energy storage systems to solar plants and wind plants, where geographical spread plays a role. Now, I'm pretty much going to run through some of these introductory slides because I'm sure in the past three days you've been hearing this time and time again in various features or formats. We all know the system is transforming, both bulk power system connected and distribution connected inverter-based resources are coming into the system. And what that has resulted in is it's resulted in what kind of services we are expecting from these resources as they connect to the network. The service is evolving. Initially, when we had the synchronous generator-dominated system, the expectation from an inverter-based resource or an IBR, as I will refer to in this presentation, was pretty much unity power factor, minimum fault right through. If an event occurs on the system, either disconnect or don't do anything because the rest of the system will handle it. So don't be a nuisance on the system when an event occurs, and just provide the active power that you want to provide and do nothing else. But as we've had more inverter-based resources coming into the network and we get increased levels in pockets of the network, pretty much the needs have increased to having automatic voltage control, some form of frequency response. Predominantly nowadays, it's downward response because of MPPT operation, so respond for over-frequency events, although the capability can be there for response to under-frequency events, but utilization of that capability oftentimes will be dictated by market mechanisms and market practices, which for the sake of us all remaining sane, we won't go into and keep the discussion on a technical level here from a control system point of view. And then pretty much improved voltage frequency right through characteristics, which also Pukraj spoke about as defined by different grid codes, and that can vary from one region of the world to another region of the world. And if we go towards a network in the future where we pretty much have IBR dominated systems, then the needs that we want from these resources are just going to keep evolving and keep going to becoming more. So fast frequency response, Nick touched upon other aspects related to maintaining system stability, and pretty much looking at an operation which doesn't rely on synchronous generators being present. So the services that we have got used to from synchronous generators providing, either inherently, naturally, or because of decades of changes and lessons learned. So it was not that one day Edison had the light bulb, or Tesla devised his rotating magnetic field, and immediately the next day we had our power system, which is operating as of today. There have been decades of experience and lessons learned, which has resulted in the state of the network that we have today. And that's how we will continue moving forward, that the services that we have relied upon for so long from synchronous generators, we would have to start replacing them either in an equivalent form or in a better format from inverter-based resources. But that's easier said than done. I mean, this kind of talk is more about saying that, hey, let's get a policy and get this services in place. But there are significant challenges, there are nuances involved for these inverter-based resources to provide this kind of network. So in the past, we've had this, I like to have this cartoon figure here because it kind of shows what we're dealing with. In the past, we've had this synchronous generator-dominated system. It's been a very stiff system. It's not very easy to move the system around. Even small island networks, they might move more relative to a large network, but still the movement is not, it's not very easy to push the system around when you have a synchronous generator dominated system. And if an IBR injected current into the network, then it didn't really move the system, right? The sensitivity of the network towards the injection of current from an IBR was pretty low. But at the same time, if the network or the system itself moved, kind of like the tail of the dog, the IBR would move around with it, but with like a stiff tail of the dog, not a weak spaghetti string tail of the dog. And what happens is this kind of relationship wherein there is a rigid relationship between the IBR and the system, and the system, if the system moves and the IBR moves along with it, has been there since day one when wind turbines were introduced into the network. That kind of a behavior recently we have started labeling as grid following. It was always there, it's just the label has been attached recently to this behavior. Now, in contrast, as we move towards a system which will now be dominated by inverter-based resources, firstly, there's increased elasticity. So there's more flexibility that's brought about in the system. There's less resistance to movement. You can move the system around faster because it's pure electrical signals that's just moving around the network. And now here, any change in injected current from this inverter-based resource towards the network can cause this network itself to move around. And the movement of this network will itself cause the IBR to move around. So now you have a feedback cause and effect relationship wherein the change in injection from an IBR will cause the system to move, and the movement of the system will itself cause the IBR to move. So essentially you have a two-body problem now, wherein previously you had only a single-body problem. And this kind of cause and effect relationship is what causes an issue, or what can cause an issue when an IBR is expected to deliver certain services to the grid, because this is happening in time scales that are in milliseconds. And that kind of a scenario, that kind of a phenomena is what we define now as the system becoming weaker. It's not that the system is really physically becoming weak, so to speak. It's more about the effect of the system, the effect of the sensitivities are what's changing. So then we raise the question, is weak grid something new? Is it only because of IBRs that we have come to the notion of weak grid and this was never an issue before? But that's not the case. If we go back to our first principles, go back to simple Kirchhoff's law and have a single machine infinite bus kind of a network, then we've always known that irrespective of what the source is, this can be a synchronous machine, this can be an inverter-based resource, it can be any other kind of source, irrespective of what the source is, and as long as you have a network which is connected to the source, we can always define a weak grid that if either the physical impedance increases or the apparent impedance increases, and there's a nuance between physical impedance and apparent impedance because that relates to the relationship of voltage with respect to current. But if this impedance increases, then pretty much the sensitivity of voltage to this current injection will increase. And the greater the sensitivity of this voltage to current injection, the weaker is the system, because any stabilizing impact that this infinite bus could provide here will not reach this network. There's weak coupling, there's an increase in electrical distance, which is not necessarily the same as increase in physical geographical distance. It's the electrical distance increase that's what's more important and what we need to worry about when we speak about weak grids. But this has been the conventional notion of weak grids. We can, from an inverter-based resource perspective, we can also define weak grids from this other two scenarios also, wherein we have a high rate of change of frequency, or we have just this high sensitivity of current to voltage, voltage to current, and we have low short circuit MVA. And sometimes these are mutually exclusive, sometimes they are interdependent on each other. But this aspect of weak grids, we've known this from synchronous machines, when we've had hydro turbines connected far away from the load centers and they push power through long lines. This has always been known. It has actually led to the development of power system stabilizers because the excitation systems would try to maintain synchronizing torque, but they would lose out on damping torque. And then we would develop power system stabilizers in order to stabilize that network. And similar approach can be used for inverter-based resources through power oscillation dampers, but there are other nuances involved there depending upon whether it's a reactive power-based damper or an active power-based damper. And some of that can be quite complicated to design and even complicated to control. But that's where evolving research is required in this notion of damping out oscillations and increasing the stability in a weak grid. And the next thing, I'm sure I saw Julia was on the presentation agenda. She would have also covered this about how we've had places like ERCOT where they've had increased build out of wind and solar, especially in the Panhandle and western portion. They've also had increased solar in the southern region of Texas. And what that results in is pretty much their conventional synchronous machine fleet, which is based around the central and the coastal regions, is now have to retire. And you have to have projects which are pushing power, gigawatts of power, tens of gigawatts of power, right from the Panhandle region, going into the other regions of Texas where the load centers are. Similar things happening in South Australia, wherein you have a weak stringy network, and what you end up with is the way in which you can deliver this power in terms of having a stable response to the system. And this is one of the ways, or one of the solutions that we can provide, is grid-forming inverters. Now, one thing let me mention right at the outset is we should not have a notion that grid-forming inverters is the silver bullet and it will solve every issue that is there. There are issues that can come up with grid-forming inverters themselves that we know of today. There are issues that we don't know of today that may come up with grid-forming inverters. And there are other solutions that can be used in collaboration with grid-forming inverters that should be utilized to bring about economic solution that maintains energy efficiency and reliability of the electric supply. So with that said, let's dive a little bit deeper into what really happens. So again, these are things which you may have already heard in either the workshop that has been happening or just in your research work, but I like to take a step back and think about this from this perspective because it helps us put the problem that we're facing into a right frame of mind, wherein a synchronous machine has inherent electromagnetic coupling to the rest of the grid. And that electromagnetic coupling, which the synchronous machine has, is in effect a synchronous machine's phase lock loop. It's just that it is naturally developed, it's naturally evolved based upon rules of electromagnetism. But an inverter-based resource does not have that. It has to have electronic control, at least a conventional synchronous machine, not some of the newer concepts. But there is a conventional control that uses phase lock loop, which essentially tracks what the angle of the grid is, and it has to lock on to that angle quite fast in order to inject its current into the network at a particular reference. So it uses this phase angle as its reference, and it needs to keep note of that reference at every point in time in order to satisfy its current sensitive IGBT ratings so that it can inject the amount of current and power that is needed into the grid. So what happens, again, if we take our first principles diagram, but now here, instead of looking from the source into the network, let's look at from the network into the source. So if we now look into the inverter-based resource, the entire set of controls of an inverter-based resource can essentially be boiled down to the simple equation, wherein you're looking at Kirchhoff's law and Ohm's law from two different sides, where the objective of the inverter controls is to inject a certain amount of current. It defines that current based upon power references and based upon the voltage. So supposing you have a power reference, and let's recognize that there are nuances involved here when it goes to actual current implementation. But if you look at it from 10,000 feet level, ultimately it boils down to this generalized setup. So if you have a set of power order that you want to inject, you want to know what's the terminal voltage that you can measure, and you also want to know what's the phase angle of that voltage, because that's what is your reference. And based upon that, you can generate a current reference that you need to inject into the network. At the same time, how much ever we like to have a notion that an inverter is a current source, pretty much all our inverters that we use for solar and wind and battery, they are voltage source converters. They have a DC capacitance, they have a DC voltage, and as a result of which you generate an AC voltage. A current source inverter is what's sometimes used in motor drive applications, where you have an inductor on the DC side, which serves as a current source, and then you translate that into appropriate currents that the motor drive releases out. So our inverters that we use for, or our converters, if you can say, that we use for solar and wind, are pretty much voltage source converters, which means that the current that gets drawn out of the inverter depends on the network voltage. So if we do nothing to this AC voltage, which is generated by the converter, if the voltage on the grid side changes, let's say the voltage on the grid side reduces, the current drawn out from the inverter will increase, because that's how Kirchhoff's law works. Just because we have an inverter, we don't abandon Kirchhoff's law on the network. So the current that's drawn out by the inverter will increase if the voltage changes. But the inverter is a current sensitive device, and all conventional controls are geared towards the fact that to fight this increase in current, as long as that increase in current is not aligned with the power objective that is to be maintained. So in order to ensure that the increase in, or the change in current from the inverter output due to a change in the network voltage is minimized as much as possible and is aligned with the reference current, what the inverter needs to do, or what the controls need to do, is they need to change this value of the AC voltage generated by the inverter. So if V and phi reduces, reduce E and delta proportionally so that the current doesn't change. And if that can be done, if that goal can be achieved in a suitably fast time frame, then pretty much I can still try to meet I reference and meet its power order. But in order to change E and delta, in order to change this, what it needs to do is it needs to track phi quite fast and accurately. And at the same time, it also needs to have a current controller that's changing E and delta quite fast and accurately so that it can meet this objective. So there are these two fast control loops that play a crucial role in how an inverter-based resource interacts with the network. So it injects control current, we have defined that. And in weak grids now, we've seen that there is a highly sensitive voltage here for changes in terminal current. Now, a control loop, as folks have already mentioned, needs some time to track something. A control loop cannot infinitely fast track a reference. And as it's tracking that control, the change in quantity, there can be a mismatch in what current is being injected. But we already saw previously that there's a cause and effect relationship, that if a change in current is going to cause a change in voltage, then what the inverter controls were tracking is now tracking a new reference or a new change, which can cause a further change in this current reference. I like to think of this in a way one of my controls professor explained it to us in school, that assume that your eyes is your eyes are your control system, are your sensors and your control system. Your brain is what you want to meet, or what the ultimate objective in the plant, and the reference movement is a finger moving in front of your eyes. If you move your finger slowly in front of your eyes can track your movement of your finger very fast, and your brain recognizes that the finger is moving, and it does that very fast. It's almost instantaneously. That is a good control system, or operation of a good control system in a strong environment. that the reference quantity that you are tracking is moving slowly, that is voltage moving slowly, and your control system, which is your eyes, and is able to track that movement very fast and register that the movement is happening, and your brain recognizes that, hey, this movement is happening, let's keep tracking the movement. But if you move your finger fast in front of your eyes, just move it up and down very fast, what ends up happening is you soon become dizzy because your eyes are not able to keep track of your finger movement. So your voltage, which is moving fast, the control system is not able to keep track of that, and you become dizzy, which is essentially what can happen in an IBR, that control loops can become unstable. And that's the core challenge that conventional inverter-based resource controls can have in order to meet this provision of services in a system that is increasingly becoming fast-moving. A fast-moving system by default is not bad. A fast-moving system is bad if it's a synchronous machine-dominated system. If it's an IBR-dominated system, a fast-moving system is not necessarily bad, as long as we have the ability to keep track of that fast-moving system and make decisions in that fast-moving system. So two possible ways, and here again, it's by no means a comprehensive analysis. There's hundreds of different ways that are there in literature. All this is meant to signify is that things are changing, things are evolving, and two possible ways that we can talk about in terms of conceptually reimagining the way inverter-based resource controls are created, are actionable, and so on, is just not allow the E at an angle delta to vary fast. The whole issue was that we wanted E at an angle delta to vary fast. Just let's not allow that. Let's allow it to vary slowly as a function of voltage or power. What that will result in is you will lose instantaneous control of current, and you will only have control. You can only get control of current, in a really fast way if your current hits its limit. If you still want to maintain tight control of current, you cannot have this relaxation. You can still have it to a certain extent, but there are limits to which you can have this relaxation. And the other way is to just go back to the front end or the back end of the control loop itself. Is you can change, instead of having rigid P and Q that you want to inject into the network, relax the rigid limit or the rigid rule, and instead allow P and Q to vary in terms of changing conditions on the grid. And now you no longer have a rigid moving system, you have a flexible system itself with a flexible grid, and all our laws of droop and stuff like that can come into play, while you can still maintain control of current continuously. Again, have to preface this that there are nuances involved here. I know a lot of you will be doing control system design, they will be doing control system tuning, and all those nuances are very important. And we're not trying to belittle those nuances. They're important to be recognized. It's just here that we're taking a high-level conceptual view of what can happen when we are reimagining these controls. And if we have that, we can bring about increased behavior or increased stability of these resources in a low short circuit system environment. We can have the control system be stable to high sensitivity of voltage to current, and we can have control systems be stable in terms of high sensitivity of rate of change of frequency. Now, Nick spoke about fast frequency response, inertia-based frequency response. Pukraj also spoke a little bit about that regarding the grid codes and IBRs participating in frequency response. So let's take a little bit of more insight into that. Let's focus on that a little bit more and take a look at how frequency response is derived, or what's the role of frequency in a conventional system. We've already noted down that there are electromagnetic properties of the network, and what that results in is that the machines, they lock onto the network. There is a link between the mechanical speed, the mechanical frequency, if you say, with respect to how the machine rotates. There's a inherent now electromagnetic link between mechanical frequency and electrical frequency, and there is a link between the electrical frequency of the network and mechanical frequency of the load. So predominantly induction motor load. So because of this link that is continuously maintained across the entire spectrum, a change in one of them will influence all the others, and we can have a closed loop system where essentially we have this notion that if load reduces, frequency will increase. If load increases, frequency will reduce, and there is a closed loop system that has been generated, which is all linked to each other. And essentially, we can govern that speed by the speed of the rotating machine. Now, this is a figure you would have seen many times. Let's just look at it again, that in this kind of a scenario, when all sources are synchronous machines, then you have an arresting period of frequency and you have a recovery period of frequency. And if you have a reduced inertia in the system, you have a faster rate of change of frequency, and you can have a faster rate of rise of frequency also if everything else is the same in the network without changing anything else. And this value of the nadir that you have depends not only on the inertia, but it depends on the time constants in the active power control loop also. So there's a significant difference in the way in which a coal power plant delivers its frequency response versus a gas power plant delivering its frequency response versus a thermal power plant delivering its frequency response, because the time constants in that active power control loop are different between these resources. So that also plays a role in where the nadir of the system lies and meets. There's a very nice graph in Professor Kundur's book which shows these differences between these different types of resources and the kind of response that they provide, which really sheds insight into how we can think of frequency response, not just from an inverter-based resource perspective, but from a system-wide perspective. But all that said and done, what changes when we go to a 100% inverter-based resource system? The first thing that happens is if there's inverters only on the source side, there is now a break in the link that we had generated with respect to frequency. There's no longer an electromagnetic link between a converter control and the electrical frequency. Of course, we can artificially create a link. We can do anything with the controls, but there is a break in this link, which means that one can redefine, one can rethink of what is frequency in such a system. A converter can really operate in a wide spectrum of frequencies, whereas machines cannot. Machines have turbine blades, they have all that which impose a restriction on how the frequency is. But in converters, especially solar, type 4 wind, battery energy storage systems, we have more freedom in the frequency range in which we can operate. And that kind of freedom and flexibility that we have, also recognizing that there is a break in this link here, we can now ask the question that can we leverage this to bring about superior frequency control? Should we still be restricted to our conventional notion of primary frequency control and secondary frequency control with the traditional curves that we have? Or can we go about having a superior frequency control? There are many documents where we actually speak about the fact that a frequency response ideally is an L-shaped response, wherein you pretty much have a drop in frequency and then it settles at a value which you know that value can be above UFLS. So that kind of an ideal frequency response, can we achieve that now with inverter-based resources, or can we even go towards a better frequency response, is something that we can think about from a control system point of view and a system operational point of view. But there is a philosophical question here, that just because it can be done, should it be done? There are a lot of things here that we can achieve with inverter-based resources, but just because we can achieve it, do we really need to do it from the sake of a practical point of view, or does it only remain as an academic exercise that, hey, we can achieve this? So it's nice to take a step back and see that why do we still need frequency control? What kind of devices require this kind of frequency control in the system and the tight range of operation? And there are also things like motor drives, transformer magnetics. There are a lot of GPS clocks that define on frequency. Sorry, not GPS clocks, but other clock systems that depend on frequency of the network. And there will still be some machines on the network, so there can be torsional stress on those machines that may require traditional frequency control. But At the same time, we can do it in a better manner because the same motor drives can offer superior control and flexibility. Transformer magnetics can change with smart transformers or power electronic transformer devices that are being developed. There are power flow control devices along the network that we have. There's increased observability, so we can get wide area control into the picture. So there are these two conflicting views that can be used together to bring about a better operation in such a network. And that's some of the research work that we've been doing, looking at operation of such a network. That if you have a conventional network where you have this traditional frequency response that you see and you know, wherein you reach above the UFLS for a large disturbance and then you recover. But in the same network, if you have the same capacity, same headroom available, but you replace synchronous machines with inverter-based resources with the same amount of headroom, you can utilize a distributed slack bus concept, wherein distributed slack bus, we traditionally know it from power flow. You can apply that distributed slack bus concept into dynamic domain also and bring about a sharing of power that then results in a much better frequency response or frequency control. It's even much better than the ideal droop response or L-shaped response that we have. And there are nuances involved there. It's not that it's always stable. It can become unstable in the way synchronous machine controls can also become unstable. So control design and tuning play a very important role in this kind of a scenario. But just the fact that they are zero inertia sources doesn't necessarily mean we have to artificially introduce an inertia component into it. We can get a much better response. Yes, there is a faster rate of change in the initial few milliseconds, but it all depends upon how that rate of change is being used or how that rate of change is being noted and for what purpose is it being noted. And if we take care of that initial aspect, then we can get a much better system. And in this kind of a paradigm wherein we have reached essentially our steady state frequency within few seconds of a disturbance, throws light into how now different balancing areas may have to evolve. Our traditional notions of the fact is that primary frequency response will bring the frequency to a steady state of nominal value, and then secondary frequency response kicks in to bring the frequency back to nominal value, to bring tie line flows back to nominal value, and different balancing areas, they then come back to their pre-disturbance value, except for the balancing area in which the disturbance occurred. So balancing areas may have to evolve. The way they operate may have to evolve. They might still have an initial change of disturbance, but you can ensure that balancing areas still maintain their way of operating in terms of going back to their pre-disturbance value, except the balancing area in which the disturbance occurred. But what this will mean is it may be based on the visibility that an operator has. Sometimes the operator may have a low refresh rate SCADA, which means that if you have this kind of frequency control, they would not see the frequency deviating, they would only see tie line flow changing. So is that acceptable in a system where you know the frequency has been brought back to 60 Hertz, but you didn't have visibility of it, but you have visibility of tie line flow? Can there be confidence that's brought about in such an operation that an operator can then feel confident that the system is behaving as expected? It will have an impact on control performance standards. Here in North America, NERC has standards called control performance standards, over which each balancing area is evaluated in terms of how much they contribute to system disturbance and how much they maintain their tie line flows and meet the requirements of the system. So if that kind of an operation is brought about, then we might need changes to these control performance standards. And that's an evolving research topic. Speaking about standards, we can now go into the aspect of the draft IEEE 2800 standard. Some of you may be aware that the standard is still being drafted right now. It's based upon IEEE 1547, but it has its implications are for bulk power system connected resources. And it has an aspect about primary frequency response, essentially defining amount of reaction time or rise time and settling time with respect to the different resources and how they respond, while stating that they should be as fast as technically feasible. Now, this kind of a definition, while it's good in a context of how we understand it and how we might take a perspective of it, there are nuances involved here which need to be considered, especially when you look at large solar plants or large wind plants, where communication delay can play a role between the plant level control and the device level control. So depending upon how you have these two hierarchy of control structured, you can have different objectives for a plant level versus device level. And depending upon the delay of control, you can have very different responses in trying to meet the same objective of a future power system, which then have to be considered. And it comes back to that as fast as technically feasible. What is technically feasible and what is not is where more definition might be required. So as a simple example, if you consider a network where you have a plant controller which is providing frequency control, and then there's communication delay, which for the purposes of this discussion is not represented as a dead time delay, but represented as a first order time constant, just to make things simpler. And if you have this kind of delay being introduced into this control path, then if you consider a system of a very small system with just around 9 inverters and there's amount of headroom available, and if you consider a large disturbance where the loss of load is around 40%, then depending upon the communication delay that you have, you can either get a stable response, which is the blue curve, or you can get a very bad response, which is the green curve, which although looks to be damping out, is way out of our performance metrics that we have. And interestingly enough, the inverter which caused an issue by having this large control delay was not in the weakest portion of the network. It was actually in a strong portion of the network. The inverters that were in the weak portion of the network were fine, but the moment we introduced a larger amount of communication delay in the strong portion of the network for this particular network was when we started having issues. So we might ask a question that, okay, can we overcome this communication delay by implementing frequency control at the device level instead of the plant level? And this is where the 2800 standard again comes into play. That supposing you consider the scenario wherein you have a system where you have, let's say, 2 inverter-based resources, and this is a 100% IBR system once this equivalent source disconnects. So if you have this kind of a network, then for 2 different ramp rates, and this is where it goes back to Nick's comments about there are very significant or very realizable impacts that happen in changing active power on the grid inverter side, because that can translate back to what's happening on the mechanical side, and that needs to be considered when we are planning the system. So if you consider a network wherein this kind of a response and you put a step change in frequency, so you reduce the frequency by 0.2 hertz to introduce the step change, but with 2 different ramp rates, then according to the standard, according to the draft requirements in the standard, both responses are equally good for the system. Both responses meet the required rise time. Both responses meet the required settling time. The effect of the lower ramp rate is felt here in the red curve and the corresponding green curve. The effect of the larger ramp rate is not felt in these 2 regions. The phase lock loop has a time constant of roughly 200 milliseconds here, which is why, although the step change in the frequency happened at 3 seconds, you see the response coming in only around a couple of hundreds of milliseconds later. So both these scenarios, in a strong network, they meet the ramp rate requirements, they meet the requirements specified in the draft standard. But the moment you disconnect this infinite source, the moment you make this 100% inverter-based resource network, only one of the ramp rates is suitable for that network. So the moment you disconnect the infinite source, which is the infinite source is disconnected here at 2 seconds, then if you have a 10 per unit per second ramp rate, you get a good stable response, and there's a subsequent load increase that happens here. If you get, and this is with the same controls, right? No control changes are made on the inverter-based resource. They still have their phase lock loops. They still have their active power controls. They have everything the same. It's just that the effect of the ramp rate plays such a role. You can still go down to 5 per unit per second ramp rate, but the 1 per unit per second ramp rate, which in a strong system showed a good response, will make the system unstable when you have a weak network. Where this plays a role is it depends upon the type of resource that you are planning in your system in order to get a frequency response from the network. And that kind of planning should be taken into account when we are planning for the future network, especially depending upon the source that is providing this resource. So if you have a battery energy storage system, you can probably tolerate higher amp rates. If you have wind energy systems providing this, you may not be able to tolerate this kind of a amp rate. But where one can then play a role here is that it depends upon the number of resources that are providing this kind of response. So the same network that we saw previously, if you make the 100% network come about at 2 seconds, if you have two plants, two inverter-based resources providing a ramp rate at 5 per unit per second, you are stable. If you have 3 plants of 100 MVA each providing a response at 2 per unit per second ramp rate, you're still stable. So essentially, if your resources have a lower ramp rate, that let's say like wind turbines, which have lesser flexibility to move around in the mechanical space as compared to battery energy storage systems, then you might need to have more resources to provide the same amount of response to the entire system. And this kind of a criteria is important to recognize as we are planning a new system, as we're getting more resources, because if legacy inverter-based resources do not provide any kind of response, then there is additional burden on the new inverter-based resources to provide the response. And if they are not capable, then you need more newer inverter-based resources to take upon that burden to meet the same system. And the same thing translates to voltage control also. The stability of a network can depend upon whether you have plant level voltage control and device level reactive power control, which is what is done in a lot of conventional inverter-based resource plants today, versus plant level voltage control and device level voltage control, wherein you have a hierarchical voltage control in place, and that can help bring about improved stability. As this shows by one of the examples that we did, wherein you have a solar plant, a large solar plant of 800 megawatts, shipping power through a 350 kilometer long transmission corridor to a grid, and then we disconnect the grid, thereby creating a 100% inverter-based resource network. So the frequency control is implemented at the device level with a high ramp rate, and we check 2 scenarios, wherein with only plant level voltage control and with additional level device level voltage control, assuming plant level controller has a realistic sampling time or a conservative sampling time. And here we introduce a dead time delay between the plant controller and the inverter control. And depending upon having this types of hierarchical voltage control, you can see the impact of the delay here in a strong network, where you again do a step change in frequency, where you reduce the frequency by 0.2 hertz, and you can see that the blue curve is where you have only plant level voltage control, and you see the slower voltage response. You see the effect of the sampling and the dead time happening here at 100 milliseconds. Whereas if you have device level voltage control, also you have much better voltage response. You see the 500 millisecond delay that's happening here because of the plant level control. But if this is the kind of response in a strong network, what can you expect in a weak network? That is when you disconnect the infinite source, is something like this. Here from these curves, we don't immediately see any instability because the inverter-based resource is a single source in the network. In the resultant network, it has nothing to move against because it is a static load. But if you see the plot of frequency for the scenario where you have only plant level control and no device level control, you immediately see that the phase lock loop has saturated. But if you have good device level control also, you can actually bring about a good stable response of the system. And this has implications in how the entire system will behave. So with that, closing off this talk towards the end, that how do we start defining future inverter-based resources? From a system planner perspective, it's important to define these services that the inverter-based resource can provide from the perspective of the performance of the inverter and not from what's inside the black box. As long as we can meet this performance, and as long as we can help write this performance into grid codes that can help manufacturers and vendors design their equipment and help provide that while all the time that we are maintaining equipment limits, and that while we are meeting acceptable metrics that we have. And if we implement all this kind of rules and these, we have this issue wherein if wind plants were operating greater than 70%, then for an N-1 event, which for traditionally the system has to be stable for greater than 70%. So for 70% operation, everything was stable as shown by the green curve, but greater than 70%, close to 99%, pretty much everything was unstable for N-1 event. But by adding on this frequency control and voltage control into few select IBRs, we didn't have to do it on all the wind turbines. We just chose few select ones. And by adding on this control to them, we could increase the export from this region by 1 gigawatt with everything else remaining the same. So ramped up the IBR percentage, take them to 99%, reduce the amount of synchronous generation, reduce the load and increase the export. We could increase the export by close to 1 gigawatt by bringing about these increased controllers into the network. And taking this to 100% is some work that we did around 4 or 5 years back now, wherein the entire Western interconnect of the North American power system, which is a 169 gigawatt system, we were able to operate or show the response of that system from a simulation perspective, that if we have these requirements which are very well defined, then we can then develop a set of IBR controls and models that will ensure that 100% inverter-based resource network can actually operate and can actually be a stable network, both numerically and from a control system perspective. So with that, coming to the end, that the inverter-based resources are highly flexible. We can take advantage of that. We don't need to stick to the synchronous machine paradigm. But with great power comes great responsibility, as Spider-Man's uncle said, that we have to be careful at how we utilize this flexibility that we have from inverter-based resources. Fast response is not always good. Fast response can cause instability in the network. But at the same time, we want these inverter-based resources to be as fast as technically feasible. So there's a lot of planning that needs to go. Important to recognize that communication delay in these large plants can play a role. But if we have this kind of networks designed well, and if we take these into consideration, it is possible to achieve a 100% inverter-based resource network, while also looking at where in the network are different resources and services coming from. With that, Damien, that's the end of my presentation.
Thank you very much, Deepak. I suspect that we might have one or two questions. I'm just wondering that before we get to, I suppose, a true 100% IBR system, we're going to get, say, for example, a high PV system where you might have 100% IBR during the daytime, but then at night you might be bringing on your traditional plant. So does that produce particular new challenges of sort of switching between 100%, switching between 100% IBR and what you might call traditional operation on a regular basis?
Absolutely. It not only brings about challenges with respect to controls and switching, what it also does is it actually brings about challenges with other topics that we don't associate as control engineers. It's more about resource adequacy, flexibility. Are there enough reserves available? Can we incorporate a probabilistic reserve evaluation framework? Brings about those kind of topics also into the picture, because now you have to consider the ramping rates of different plants. You need to consider how to schedule them as you transition from, let's say, a daytime scenario where you have high PV to a nighttime scenario. So it's not in those kind of frameworks. It's not just the controls and shifting of the network that plays a role, but even these other associated topics that will have even more importance.
Okay. I suppose I'm also wondering about, just at a very basic level, the definition of grid forming. And, you know, what are your thoughts about the definition of grid forming, and how do you avoid that definition sort of creeping into other things, such as, for example, black start being part of grid forming? So
and this has been debated quite a bit. Nick and I have also been involved in some of our recent work where we collaborated to kind of frame a definition. And at the outset, there's going to be no definition that pleases everyone. There's always going to be some amount of disagreement, and which is healthy. That's how we have more debate and conversations. But what we've been taking this position from an EPRI perspective is it depends upon who is doing the defining and what are they going to do with the definition. So, for example, if it's a system planner or a system operator who's doing the defining, and then if they are going to use the definition to determine which vendor's product can come into the market and which vendor's product cannot come into the market, then the definition has to be solely based on performance. It has to be solely based on meeting a set of performance criteria, meeting a set of required performance that they can measurably track without knowing what's happening inside the inverter. So they should have a definition from this perspective that give me X, Y, and Z service. I don't need to know exactly how you are doing it, as long as you can provide that service. So that's from a system planner perspective, that's the definition that needs to be used. But if it's a definition being used, let's say by an OEM vendor in how they design their controls, then they can have internal definitions that product X has control algorithm Y, we will call that grid following. Product Gen X has control algorithm Gen Y, we will call that grid forming. Then there it depends, the definitions can go into the control realm also in terms of the way we define grid forming. Now, then there's the other definition from a conceptual perspective, that how do we conceptually understand what is grid forming? How do we conceptually maybe educate what is grid forming, what is grid following? That's something that we've been working on with some of the, especially through ESIG and through IEEE, looking at the fact that the voltage is maybe the voltage phasor is constant in the subtransient time frame, or you don't allow the current to change in the, you don't allow the voltage to change in the subtransient time frame, but allow the current to change in the subtransient to transient time frame. So there, that you can have a type of conceptual definition. So I think this grid forming versus grid following, the definitions, it will there's always going to be differences depending upon the view and the perspective that we have. Our recommendation to some of our EPRI members is that if they do have to use a definition, don't always assume that the person to whom you're talking has the same interpretation of the phrase as you have. So always better to go into a little bit more detail to explain. So just saying grid forming to a vendor doesn't necessarily mean that the vendor has the same perception of grid forming as you have. So better to explain what you mean by grid forming, and also better that the vendor explains what they mean by grid forming in terms of the services that they can provide to the network.
Okay, so around the world, there are a number of sort of well-known examples where grid forming has been implemented, particularly associated with batteries. Mm-hmm. I'm wondering what sort of timescales you think we're talking about before grid forming becomes common in power systems, or either becomes part of grid code requirements or system service arrangements, or you know, how quickly will we go from sort of the research and you know, asking questions phase to this being a common thing?
Yeah, I don't know if there's a way to really put a number to that as to how soon or how fast. There are places like in Hawaii where they have already started framing some requirements or definitions for grid farming in their grid code because they're seeing such a influx of battery energy storage systems. There are places like even National Grid has released the Pathfinder, which drafts some framework for grid farming. Places like Australia where they're looking into it. I think at the end of the day, it comes down to again going back to the service that they can provide, and if as the systems evolve, we will see a need for maybe system strength services. We will see a need for inertial response or fast frequency response kind of services, and that will help define as places transition. So large systems like maybe like the US Eastern Interconnect or Western Interconnect may not require this even in the next 10 years because their percentage of inverter-based resources may be restricted to a pocket, whereas other interconnections like Hawaii or, Hawaii is not in interconnection, so to speak, but isolated systems like Hawaii or interconnections like ERCOT, they might start requiring this faster, but it may be hidden, right? It depends upon what are they requiring it for. So while one might say grid farming service, it might also be come across as robust voltage control, stable voltage control, and those kind of requirements also may come into play. So long story short, I would say that next 5 years, we will start seeing more of this coming into play into grid codes, either in an explicit format or an implicit format, and it will continuously evolve as we go further from there.
Okay, thank you. So it's late on Friday afternoon, except for Deepak and Nick, where it's early morning, but it's sort of late Friday afternoon. So I think I will sort of call things to a close. So on behalf of myself, Anka, and Kaushik, I would like to thank